Section 10.5, the comparison test. We are going to cover a couple of tests in this section. That is number 1, the direct comparison, and number 2, the limit comparison test. Right? Well, so what about this section? So from now on, we will be given more funky looking series for which we will determine the convergence. However, we are going to use, come up with or relate these ugly looking series and compare them with simpler series for which they are easy to determine the convergence or divergence. So typically, we would relate this series to something like a p-series or like a geometric series, which are the ones that are very short to just get their convergence or divergence. Okay, so what's the idea? So number 1, so let's say we are to determine the convergence or divergence of this series. Well, the series right here looks like the following series. N equals 1 to infinity, and that's n squared over n to the 5th, which is equal to 1 over n cubed. Okay, what about the series 1 over n cubed and going from 1 to infinity? It's a p-test, and what can we tell about it? Converges or diverges? Converges, right? So in this case we have a convergent p-series. Why am I doing this? I mean, because ultimately this is about end behavior of the functions. I mean, if you think about the original series, the ugly looking one, the behavior of the actual series will be set only by the leading terms. I mean, the terms that are lower in degree are not going to contribute more than the leading terms, right? So ultimately it's the leading terms that determine the behavior of the values, So that's why we do this. Like, we pretend we don't have the lower degree terms, we just focus on the leading ones and come up with something simpler. For the next example, we have the square root, sigma n equals 1 to infinity of 1 over the 5th root of n cubed plus 2n plus 4. Well, in this case, we can neglect the lower degree terms inside of the radical and say that this looks like n equals 1 to infinity of the 5th root of n cubed. And well, in this case, this series is the same as saying sigma n equals 1 to infinity 1 over n to the 3/5. Alright? And again, this looks like a p-series. This is something easy to relate to. And in this case, by the p-series test, we have a divergent p-series. Right? Because of the value of p over here. Okay? And another crazy looking series right here. Well, we have sigma n equals 1 to infinity of 3 to the n divided by 7 to the n plus 9n minus 3. So of course, in the same way, we can neglect the lower degree terms. Even though these are not really degree, we have exponentials. Well, recall that exponential functions are higher in rank with respect to polynomials. So these 9n and minus 3 are not really contributing that much on the value. Alright, so in this case, we can say that this looks like sigma n equals 1 to infinity of 3 to the n over 7 to the n, which is the same as saying n equals 1 to infinity 3/7 to the n power. Now, does that series look familiar from something that we did before? What is it?
The one with the A and the R.
The one with the A and the R. What is that? Geometric series. Well, in this case, the value of R is 3/7. That's the number that gets raised to the power of n. Because this 3/7 is less than 1, then what do we have? It's a convergent geometric with R equals to 3/7. All right. So that's the whole idea, to come up with a simpler series based on pretty much the leading terms for the series that we're given. Now, what is the direct comparison test about? So in this case, we are going to have what I usually call the problem series, the complicated one, the one that we want to find its convergence or divergence. And then we have another series. We have a second series, which is the test series. The simpler one, the one that is easy to determine its convergence or divergence, and the one that we use to compare with the ugly looking infinite series. So we're going to set an inequality. Well, in the convergence case, so what we're going to do is come up with a new series. Okay, if that new simpler series converges, then we need to set up this inequality. We need to show this inequality. We need to show that our problem is less than or equal to the problem that we came up with. If it's and from there, if this inequality is true, then the original series, the problem series, will do exactly the same as the test series. For example, if my test series converges, my original series also converges. And well, a good way to relate this is we need to show that tiny is less than small. Alright, so let me give you a brief picture for this, so you can have a better visual. Alright, so in this case, okay, so we have a b sub n, which is a known series that we know that converges. That is, it's not blowing up to infinity, it's getting somewhere. I'm going to denote the graph of that sequence like this, all right? I mean, it could converge to 0, it could converge to 1, I mean, whatever that is, doesn't matter. So in this case, the newer series, the series for which we want to determine the convergence of, let me choose a different color, okay, yeah, this one is fine, has to be smaller. But also, do you see the behavior? It's also converging. So here is where we're showing that tiny is less than small. All right? On the other hand, let's say that we end up with a simpler series that diverges instead. Well, so in that case, we need to make sure that the inequality in the other direction is true. In other words, we need to show that huge is greater than big. Okay? And let me give you a picture for this. So in this case, for a sub n, we need to make sure that a sub n, our problem, yes, it's a bigger infinity than the infinity that we're comparing it with. That's what we're trying to show. So that one grows a sub n a lot faster with respect to b sub n. Which, yes, but notice both of them are blowing up to infinity. Alright? However, the problem is huge, but the one we compare it with is big. So that's the idea. Alright? You'll see. Well, I think this is going to make more sense once we set up the inequalities, once we see the examples, which is, well, let's do one. Let's do a couple. Okay, so let's determine whether each series converges or diverges. So number one, we have sigma n equals 1 to infinity of 1 over n squared plus 2. Whoops. So, observing this series, we can neglect that plus 2 in the denominator and turn the series n equals 1 to infinity to 1 over n squared. Well, so this is a convergent P series. Well, at this point you don't have to show me what the value of P is. That's fine. I think at this point it's when you're using the comparison, it's understood that you are comparing it with a convergent P series because you understand how the P series test works. All right, so no need to write a lot. So in this case, what is it that we need to show for convergence? We need to show that tiny is less than or equal small. Well, which one? Whoops. Which one is which? Well, in this case, the tiny is the problem and the small is the test series. And all we have to do here is put the quantities together. That is 1 over n squared plus 2. Is that less than or equal to 1 over n squared? Is that inequality true? Yes, that's all. That's all you need to do. Therefore, the series converges by direct, actually, let's just write down DCT, by direct comparison test. And that's because we managed to check this inequality, to show this inequality, then our original series will do whatever the test series does. So in this case, if the test series converges, then the original series also converges. Let's have a look at another one. All right. So sigma n equals 1 to infinity of 1 over 3 plus 2 to the n. Well, which of the terms in the denominator is the highest level term? 2 to the n. So we can neglect the 3. And we can have 1 over 2 to the n. Alright? And actually, okay, let me write that down. We write down that we should compare with. Also, let me know that we compare with. Alright? Because yes, a very common mistake when it comes to notation is to write down equal. No, these two series are not equal. What we're doing is comparing. Well, we get this series, sigma n equals 1 to infinity of 1 over 2 to the n. And well, in this case, is that a P series? Wait, no, it's not a P series. We have the reverse, right? The P series is n to the P value, but in this case we have a number raised to the n, the reverse. So no, it's not a P series. Is there anything else that looks similar that we compare it with in a simple way? What is it?
The geometric series?
It's a geometric series, sigma n equals 1 to infinity, 1 over 2 to the n. Alright, and what do we have? From here we have a convergent or divergent geometric. Convergent. not P series, geometric. All right, because we are coming up or we are comparing with convergent series again, we have to show that tiny is less than or equal to small, where the tiny is our original problem and the small is the test series that we use. And let's see if the inequality is true anyway. So, yeah. Is 1 over 3 plus 2 to the n less than or equal 1 over 2 to the n? True. Therefore, the series converges by direct comparison test, DCT. All right? Let's do one more. Sigma n equals 1 to infinity of 1 over the square root of n minus 4. Well, number one, again, we could just neglect that negative 4 and compare with the following series. Sigma n equals 1 to infinity, 1 over the square root of n. It's a divergent, what kind of series? P series, right? If we write this in terms of n to the 1/2, here we have the fact that this is a divergent P series. Alright, it's a divergent P series. So in this case, because of divergence, we're not going to show whether tiny is less than small. In this case, we're going to show the other inequality. We're going to show that huge is greater than or equal to big. And let's find out if it's the case. Well, in this case, the huge would be the original problem, and the big will be the test problem, the test series. So 1 over the square root of n minus 1, not minus 1, minus 4, but that minus 4 is not inside of the radical. And is this inequality true? Yes, we have more than one term in the denominator of the left hand side, but notice that 4 is subtracting, so we're subtracting in the denominator, getting a smaller number in the denominator. But what happens when we divide by a smaller number? We get a bigger value as opposed to the right hand side of the inequality. Then
on the previous page, why are both inequalities equal to? Because you have less than equal to and greater than equal to.
And
yeah, we have less than equal to and greater than equal to the n.
So that's to compare. So
yeah, but they're both equal. That's the problem. I don't see why that's unequal.
Oh yes, because we could be. I know. Yeah, you mean the equal sign? Yes. I got this question asked before, but I mean it could be the case that we end up comparing. With the same series. Let's say we come up with something simpler, but we end up comparing. I know it's weird. Yes, I would change that to get rid of the equal. Sure. All right. So, but I mean that's fine. So in this case, this is true. And well, what do we have here? We have that the series diverges by direct comparison test, because in this case we were able to show that huge was greater than big than our original series does, whatever the test series does, which in this case is to diverge. All right.